Welcome back, students. In this lecture we will see some problems on undamped fluid. So directly let's go to the question. So we have a block of mass 680 gram for 4.68 kilogram, and it is connected to a spring constant K is equal to 65 Newton per meter. Block is pulled at a distance of x equal to 11 centimeter from its equilibrium position and released from rest at time equal to 0, which means that it is released from rest means that initial velocity is 0, so v0 is 0, and it is displaced to a distance of 11 centimeter, which means that initial displacement y0 is equal to 11 centimeter or 0.11 meter. So this is a free undamped vibration case, so you are asked to find out all the parameters related to it. So starting with angular frequency, cyclic frequency, time period, then amplitude of motion, maximum speed, maximum acceleration, phase constant, and finally you have to write out the displacement function c sin omega t. After finding what is the value of c, what is the value of phase constant phi, and what is the value of omega. Right. So to start with, we'll find out the angular frequency omega is equal to root k by m. So 65 divided by mass should be substituted in kilogram. So please note, when you're using this particular equation, k should be substituted in Newton per meter and mass should be substituted in points kilograms. So substituting, you get the value 9.78 radians per second. So once we have the value of omega, you can find out the cyclic frequency f is equal to omega by 2 pi. Okay, so 9.78 radians per second divided by 2 pi radians. We have f is equal to 1.56 per second or 1.56 hertz. Once you have the frequency, you can find out the time period as inverse of frequency. So t is equal to 1 by f. We have time period as 0.64 seconds. So next one is we have to find out the amplitude. So amplitude is nothing but a square plus b square, where a square over a is equal to y0 and b is equal to v0 by omega. So here v0 is 0 and y0 is 11 centimeter. So substituting, we have c is equal to 11 centimeter. Maximum velocity is given by c into omega, so 11 centimeter, which is 0.11 meter multiplied by omega, so 9.78. We had maximum velocity is 1.075 meter per second. Okay, maximum acceleration will be given as minus c into omega square, so minus 0.011, which is c multiplied by omega square. We have maximum acceleration as minus 10.52 meter per second. Okay, phase constant you could have either found out by using tan inverse a by b or tan inverse y0 by v0 by omega, so which implies alpha is equal to pi by 2 radians or 90 degree, right? Also you could find out the same thing by using the initial condition. So initial condition, when time t is equal to 0, displacement t is equal to y0, so it is gives an expression 1 is equal to sin omega into 0 plus alpha, so sin alpha is equal to 1, so alpha is equal to sin inverse of 1, which is pi by 2 radians or 90 degree. Okay, so we have found out phi, we have found out the amplitude c, also we have found out the phase angle alpha. So we can write the displacement function now as x of t is equal to c sin omega t plus alpha, right? So 0.11 sine into 9.8, which is omega multiplied by t plus pi. Okay, so we have the displacement function as well. Now let's see another problem. So here we are asked to find out the natural frequency of the system shown in the figure, consisting of a weight of 50 Newton. So weight is given 50, which means that mass is equal to 50 by 9.81, and it is attached to cantilever through a spring of stiffness K2 is equal to 20 Newton per meter, and also there will be stiffness associated with the beam as well. So in order to find out the stiffness of the beam, we are given cross section, length, and the Young's modulus of the beam. So stiffness is nothing but force per unit displacement. So if you know the displacement at the end of the cantilever, okay, force causing it divided by the displacement will give the stiffness K1. So K1 is equal to force per unit displacement, so P by delta. Okay, so deflection at the end of the cantilever, delta is nothing but PLQ by 3A. Okay, so now that we have delta, we can find out K1 as P by delta, so which means that it is equal to 3A by LQ. Okay, so K1 is 3A by LQ. It is in series with another stiffness, another spring K2. So the combined stiffness of K1 and K2 is going to be 1 by K equivalent is equal to 1 by K1 plus 1 by K2, right? So first of all, we will find out what is the value of K1. So keep in mind, you should substitute you're substituting the E in Newton per mm square, MPa or Newton per mm square. So you convert L into mm first. So L should be substituted as 200 millimeter. The dimension is already given in millimeter. So I is equal to BD cube by 12. So that is used here. 3 into E is already given in Newton per mm square. Length in millimeter substituted. You have K1 is equal to 4218.75 Newton per millimeter, which is nothing but 4218.750 Newton per meter, because the stiffness of spring coil is given in Newton per meter. Okay, so the equivalent stiffness can be found out 1 by Ke is equal to 1 by K1 plus 1. Okay, so equivalent stiffness is 19.9 Newton per meter. So once this is obtained, we can find out the natural frequency of the system as root K by M. So K should be substituted as equivalent stiffness and mass should be in kilogram. So 50 Newton divided by 9.81, that much kilogram. So we have omega is equal to 1.98 radians per second. See one more problem. So here we have simply supported beam, and at the center we have a load suspended by a spring of stiffness 50 Newton per millimeter. Okay, so load is given 150 Newton, so mass is 1500 by 9.81, so load is 1500 Newtons. Okay, so the stiffness of spring is given, so along with this stiffness, the stiffness of beam will also be associated. So the stiffness of beam is K1 and stiffness of spring, let's say it be called as K2. So K2 is equal to 50 Newton per meter, K1 is unknown. So in order to find out the stiffness of the spring, sorry, stiffness of the beam, what you have to do is you have to know the displacement at the center of the simply supported beam due to a point load at the center, right? So that delta is nothing but WLQ by 48 EI or PLQ by 48 EI. So K1 is nothing but P by delta. So delta is already given. So P by delta is 48 EI by LQ. So here we have E given in MPa, which is Newton per millimeter square. The dimension of the beam is given. It is B is 50 millimeter and D is 5 millimeter. So we can find out I value as BDQ by 12. L is given as 500 millimeter. So substitute and find out what is the value of K1. So we have the K1 value as 40 Newton per millimeter. So the beam stiffness and the spring stiffness is connected in series, which means that we can find out the equivalent spring stiffness 1 Ke as 1 by Ke is equal to K1 1 by K1 plus 1 by K2, right? So we got K is equal to 22.22 Newton per millimeter, and also we have a weight of 1500 newtons, which can be converted into kilogram as 1500 by divided by 9.81, that much kilogram. So we have the expression omega is equal to root k by m. Okay, so substituting the value of k and m, we can have the value of omega as 12.00055 radians per second. So that's it. That you can find more problems for practice. However, the concepts are more or less same. Okay, so you can practice more problems. Thank you.